Hello, Nubik. This is the HTM office hour. I don't even know what date it is, but we've got
February 7th.
February 7th. We don't know what date it is, but we're here to talk about some Numenta papers and take some QA from our community. I'm Matt Taylor. This is Jeff Hawkins. This is Subutai Ahmad. This is Alex Lappin. We also have Scott Purdy in the room and UA, and we're going to get going. So let me go over here to MC, and I'm going to let Jeff and Subutai talk. But while I show the papers page, why don't you guys maybe start talking about the papers?
Okay, and then we'll put up the PDFs.
Whoa,
yeah, that happens every time. Numenta.com/papers is where I'm going right now. Here we go. Make it really big. All right.
Okay, so this is a page that we just put up on our website, and the genesis for this is people are ask us where are our papers, and now we have an easy, simple page that lists all of the current papers that we're put out there or that are on.
These are peer-reviewed journal papers or academic conference papers. These are not white papers, right?
Exactly. These are more researchy academic papers, one of our goals last year and this year is to really be out there a lot more in the academic community and the research community and do a lot more publishing. So these are papers that are in various stages of being published. So we can walk through them. What we thought we'd do is show the PDFs for the various ones and talk about them, and then we'll give a sort of a brief summary of each one as a guide, and then we can take questions, or we're also
with. So you pick a paper to start talking about. I'll open it up and maybe we can browse it while we talk about it.
Okay, the big paper is the neuron paper, which is the first paper.
Yeah. I'll tell you when to start browsing, okay?
Okay, you tell me to start browsing. In the meantime, we'll keep it here.
I don't get to see it?
Oh yeah, you'll get to see it.
But whatever you see
what they see.
I want to see the paper.
Here we go.
Okay, so this is sort of an umbrella paper that covers a lot of what we're doing here at Numenta. Not everything. It basically covers the neuron theory and the temporal memory, but it doesn't cover, for example, spatial pooling or temporal pooling. We chose a rather provocative title, Why Neurons Have Thousands of Synapses, a Theory of Sequence Memory in Neocortex. We'll see how well that works. But it did already, MIT Technology Review picked it up out of the archive submissions. And I can only imagine they did that because of the title. So, it's not your typical academic title. Go down a little bit to there. So we're not going to go through the whole paper, but these are some of the main ideas in the abstract. We're basically in the first highlight there. We're saying like, hey, neurons have lots and lots, thousands of synapses. Why? What behavior do they enable? This is something that's really not well understood. Something HTM theory explains, but we're building upon a very well-known property of dendrites called nonlinear properties, dendritic spikes, and that's the second highlight there, saying, hey, we're just extending some existing theory about showing how thousands of synapses a neuron can learn hundreds of unique patterns. And then we propose a neuron model, which is essentially our model neuron, the HTM neuron, has, we have proximal dendrites, distal dendrites, and apical dendrites, and we have a reason for them, and most neural models do not have a theoretical reason for those. And then finally, the last highlight is we present our sequence memory or temporal memory model. So now you can just scroll down all the way, I believe, you can go all the way to the, just go to the first figure.
The first figure.
Nope. There we go. So I'm just going to walk through the figures briefly. So people in the HTM community know these pictures. Here we're just trying to make the stark contrast between a biological neuron labeled B, a typical artificial neural network neuron labeled A, and an HTM neuron labeled C, and really introducing the concept of active dendrites for coincidence detection and multiple different types of dendrites and input. Next figure. This figure is essentially, you've seen this before too, these are slightly modified from ones you've seen in presentations. This introduces the basics of our temporal memory system. As I said, we don't actually explain spatial pooling here, just doing temporal memory. Next one is an extension of that, showing multiple predictions at the same time. Next one, here's something we talked about, the role of apical dendrites in this paper, which we haven't incorporated in our NUPIC or any of our code today. but we have a theory about what they're doing, so we describe that in this paper. Next. This is something we also have shown in previous talks. We can skip over. That's the growth of synapses. We did a number of simulations here, Subutai and UA, and I forget who else worked on them. These charts are just showing some simulations of the network. The one on the left side is just demonstrating that the network can learn high-order sequences. And so we show the red line of a properly performing network learning the absolute maximum it can get on this particular problem. And then it dips in the middle there because we changed the sequences. So we're showing it's continuing to learn and recover. The blue line represents when we have a first order model where we use just one cell per column and never really learns the entire sequences. The one on the right, the figure on the right, just shows how the system performs when we kill off a lot of cells. This impresses a lot of people, but essentially up to about 40% cell death in this particular problem, there is no degradation in performance. And even after 75% cell death, which is the lower purple line, it will recover. There's no magic here. There's extra, the network is able to learn more than we've trained it, and what you're really losing is the ability to generalize. But given a particular task, it can perform like this, which is a pretty impressive thing for some people. Okay. The next thing here is a math box that Subutai did, basically walking through all the mathematics of sparse distributed representations and how they relate to the neuron. And I'm going to end this little talk about the paper here.
Okay. Okay. Let me make sure first of all that I've got the Q&A app on. If anyone does have any, there's already a bunch of questions. Yes, we are on. You don't see anything? Rick, I did send you an invite, I'm pretty sure. Sorry about that.
I just went to hangouts.google.com and it showed me that I clicked it.
Okay. Sorry about this. Rick wanted to join and I couldn't figure out how to get him to join. So that links things. It's just basically people saying they can't see anything.
Did they hear anything?
I don't know. Let's see. Can you all see us now? Or maybe I should just be asking you on the camera. Can anyone see us now? I think I meant it to start. So I don't know exactly when all these were. So someone does have a question. I think that's relevant. But I wanted to try and get to the questions later. Let me make sure that everybody can hear what we're saying at this point.
Yeah,
we can. Okay.
Works fine on my phone.
Works fine. Great. Okay, give me 1 sec. I do want to try and get Rick on here because he's always he always has something to talk about. And the way Google changed things, it makes it really hard for me to find anyone. There's Rick.
Who's in the VIP? So.
Yeah, but the thing is, I try and invite him, and all I can do is say Rick L. But he's not in this list. So I'm really sorry, Rick, if you're watching this afterwards. I can't figure out how to get you in there. I know you think it's a Google conspiracy against you, and it probably is. So. Okay, so let's, what we should probably do is go to the next paper on the list and
go back to the questions.
Did you want to go back to the questions afterwards?
Should we do, yeah, go back to the questions afterwards.
I just see one question.
If there's one relevant, do you want to address it?
That's specific to the paper.
That's not specific to the paper? Yeah.
Metabotropic. Just that we did not mention metabotropic. Did we mention it? I don't think we did mention metabotropic receptors in the.
Let's address it then.
I might have had in there one version, but
I'm suggesting adding it as a way to solve some other problem here. But did it talk about temporal pooling at all?
Did not talk about temporal pooling.
So I don't think this is related.
Yeah, I don't know. You know, it was a tough paper to write because there was so many topics we could cover, and we couldn't cover all the ones you really need to understand the whole thing. So we had to sort of pick a subset that seemed to be somewhat self-sufficient. And you know, one of the first comments we got back from the first place we submitted it was, you can't publish in this journal because you need more space because there's too much here, and you know, and you guys should write a longer paper. So that's a challenge we had to deal with. And we did write a longer paper, but not as long as we didn't want to make it go on forever.
All right, so that was John Robinson's question. Finally got through everyone. Thanks for telling me that you can now see the video. So the next paper that we were going to look at.
So the next paper should be probably the sequence memory paper. So if you go back to
and that was the second one?
Yeah, it's in your
right. Okay, so this is not the screen.
You want to
yeah, you can.
And which HTM sequence memory?
Yeah, that's it.
That's the one. Yeah. Okay.
Oh, Alex. Just trying to get out of.
And so share my screen, share my PDF. Yes.
So this second paper focuses on the sequence memory model proposed in the HTM neuron paper. And here we focus on the computational properties of the sequence memory paper and compare it with several other techniques on sequence learning problems using both artificial data set we generated as well as real world data set. Can you?
Here,
Okay, the first figure. Yeah.
I will let you control the scrolling and stuff.
So this is
So you're going to see some overlap here because we're
Yeah.
building on the
Yeah.
previous paper.
Yeah.
Just everyone knows.
because we want to be self-contained. So the first part of the paper is to describe the sequence memory model. It's a little different. So the slight difference is here we describe the algorithm in more detail in mathematical terms. But the idea is essentially the same. And the first set of experiments we run here is to train both HTM and LSTM recurrent neural networks on a continuous online learning problem, where we're generating a streaming data set using a set of artificial sequences. And
so anyway, maybe you should explain throughout this paper, we're contrasting HTM temporal memory with LSTM.
with LSTM and several other techniques.
But LSTM is the current hot thing
Yes.
we're talking about.
But we're contrasting not just on accuracy, but on those
Yes.
set of
Yeah.
properties.
Yes.
It's more of a, so like, here's what these different things do and how they relate to
Yeah.
one another.
If you audience have any questions about this paper, now would be the time to type them in. Well, I'll try and hit them after you is done.
Yeah, the goal is not to say that HTM is better than the rest of the techniques, but to focus on the set of properties it demonstrate. Here is showing that it's similar to one of the graphs in the neuron paper where we show the prediction accuracy increase as the model sees more and more of the elements from the sequence. And here we change the sequence to a different data set. And as you can see that the performance decreased initially, but then rapidly restored to its 100% accuracy, which is faster than the LSTM network for this particular example. And next, we show that demonstrate the ability to make multiple predictions by using a different data set that has multiple possible endings. Again, this property is showing in the neuron paper, but here we compare it against other techniques. And then we move to a real-world problem, which is to predict the number of taxi passenger count in the aggregated 30-minute window. So this is a real-world data set downloaded from the New York City taxi website here. And here we show a bunch of algorithms here. So this is the first version of the paper. In the second version, we also include a bunch of other techniques like echo state network and nearest neighbors. The take-home message is we have comparable accuracy than the state of the art, which is LSTM in this case, on this problem. But more importantly, we demonstrate the flexibility, which is shown in the figure 5. Here we injected an artificial change to the data by increasing the passenger amount by a certain percentage during certain hours. And both algorithms react to this change with increased error initially, but HTM decreased faster because it adapts to the change in the data set. And here's showing the error is much better than the LSTM after the change to the data set.
Can I just, it might be helpful for people watching this. We're actually plotting multiple LSTM networks. And the main reason is that LSTM is not an online learning network. Correct me if if I say anything wrong here, it's not really an online learning network. So we have to sort of fake it by doing batch training over and over again. And it makes it a little bit tricky, but you can get better results by how often you do the retraining and how much data you batch over. So we're trying multiple parameters there to get the LSTM networks to work better. But most of these changes, LSTM will match temporal memory in terms of its accuracy on an individual prediction. But in the continuous learning or the adaptive learning, and in terms of multiple predictions, it doesn't do as well. The LSTM doesn't do as well.
Yeah. So although the performance may seem similar here, the way LSTM uses data is very different than HTM did, because LSTM needs batch training. It needs to look over the data hundreds of times to do gradient descent. But HTM only needs to look at the data once in a streaming scenario.
So computationally, the HTM was way faster.
Yes.
In learning.
Yes.
You want to just go through the properties?
Yeah. So we ran these experiments to demonstrate a set of properties. We think that's critical for real-world streaming data analysis, which is described in detail in the second section of the paper. These properties include continuous online learning, being able to make high-order sequence predictions, and being able to make multiple simultaneous predictions, demonstrate robustness to both sensory noise and fault tolerance. And the last one requires little or no hyperparameter tuning. So so we show a bunch of experiments in this paper, and we use the same parameters for all the experiments.
For HTM.
For HTM.
Good.
Okay, cool.
Okay, let me get back to our next one. Now I'm going back to the research papers.
Which one's next?
Probably do the SDR paper.
And that's
on there.
this one?
No, yeah, that one.
Yeah.
But it's in that.
Right, I just want to highlight which one we're talking about so when people are watching, they can. Okay, so let's stop. That is this one, SDR properties. Okay. And back to share. A little tedious. Yeah, okay, there we go.
Okay, so this is also in some ways a companion paper to the neuron paper. This is also kind of a follow-up of a talk I did in an older paper, which talks about some math around sparse distributed representations and how you can do various scaling laws around the SDRs. This particular paper, it's been submitted to a journal, and we're waiting for review. So the hope is that it's eventually going to get published in the peer-reviewed format. This particular one is focused a little more towards a neuroscience audience rather than a computational audience. So a lot of the language here is around active dendrites and NMDA spikes and really focused on neurons. And so the basic idea here
just in contrast is the paper that Yue just talked about was more on the machine learning world. Neuroscientists don't care about LSTM, they've never heard of it, right? Yeah. So that was more neuroscience. I mean, that was more machine learning, this is more neuroscience. We're trying to balance these two words.
Yeah. And the basic idea is, we again showed the same idea of having that a neuron is a lot more complicated with active dendrites. The typical machine learning neurons do not take that into account. And we have for the mathematical model, we have a very simplified version of our HTM neuron. So it's just a bunch of dendritic segments there. And then there are various equations that kind of characterize the properties of these dendritic segments when the inputs are sparse distributed representations. So I won't go into all the math in detail. There's some pictures which kind of show you how a dendrite looks at its inputs. There's a bunch of math that sort of talks about the scaling properties of this. Let's see. we have simulation. Yeah, I'm not going to go into the details. You can read it. And then a bunch of charts that kind of show how things scale under different scenarios. So figure 4a, for example, shows that if you look at the size of the SDR vector, which in this case is the number of cells that are feeding into the dendritic segment, and you look at the probability of false positives, what you can see is that the error drops exponentially as you increase the number of cells in the population, as long as you have sparse representation. So this y-axis here is a log scale. So this is actually decreasing faster than exponentially. The A is kind of the number of active bits at a time. So if you have 64, 128, or 256 out of thousands, that's the sparsity. You can see that the error drops exponentially, or faster than exponentially. But what this dotted line shows is 50% sparsity. So if you don't have really sparse representations, then you don't get that drop in error. So this is really pointing out the importance of sparsity and the importance of having a very high dimensional
And
representation.
you're just talking about one dendritic segment at this point.
This is just one dendritic
So this
segment.
is really focusing on the sort of the properties of a dendrite, just trying to recognize a single pattern. It's a sort of more of a detailed view of a section of a neuron.
And then similar thing on B, it looks at the number of synapses on a segment and how that's affected. So again, it shows that as you get more and more synapses, the error decreases really fast as long as you have sparse representations and as long as you have high dimensionality. The dotted line shows situations where it's not as sparse, and then you don't get that drop in
This
error.
again is an exponential curve on the
Yeah.
y-axis.
It's a log curve on the left.
Yeah, y.
This was a result that's probably mostly meaningful to neuroscientists, but there are lots of experimental results that show that if you get somewhere between 8 and 20 synapses on an active dendrite, you get a dendritic spike. In HTMs, that's what puts a cell into predicted mode. And what we could show with the equations is that these equations actually directly predict that experimental result. So the gray area shows basically the regime that the experiments are in between 8 and, let's say, more than 20 synapses active at a time. And you can see that once you get past about 8 synapses, the error starts dropping. And this is about almost like 1 in a billion chance of error, all the way down to 10 to the minus 28. So this is the regime where you would get really, really low error. Anything lower than 8 synapses per segment, you'd get much higher error. And so the equations, and this curve was plotted using under lots and lots and lots of different assumptions about sparsity and dimensionality, and this is basically showing the median error. So under very loose assumptions, you can basically predict that experimental result. And then there's some other stuff in here. That's probably enough for this.
Yeah.
So it's a pretty mathematical paper, and it's pretty focused towards kind of specific neuroscience kind of audience and results.
So let's jump back and see if there's questions. We'll save that one since it's not about the paper, and we'll address the other questions that aren't about these papers at the end. The next paper, let me share once again, the research paper screen here. Which one do you want to talk about next?
Yeah, that's a good
That
one.
one, evaluating real-time anomaly
Alex.
detection.
Alex.
Okay, and that is called, which one? Anomaly detection here?
No, NAT.
Oh, this is the name. Okay. All right, so I'm going to go back and share a different screen here. This is Alex Lavin. Very good. Would you like to do the scrolling?
Sure.
There you go.
So this paper is on NAB, or the Numenta Anomaly Benchmark. Subutai presented it at MLConf in San Francisco last November, and I gave a similar talk at ICMLA in Miami in December. And we published this paper kind of around the release of version 1.0 of this benchmark. If you're not familiar, this benchmark is designed to evaluate algorithms for detecting anomalies in streaming data. And we found that this was very important both for us as we were developing HTM towards anomaly detection, but also for the larger research community, because benchmarks out there are really designed just for batch type algorithms. And streaming is important. It's going to be even more important with things like, well, Internet of Things and connected sensors everywhere. So we thought that releasing this benchmark and specifically to the open source so the community can use it would be really important to kind of spur innovation and research in the field. Let me run through a little bit of what the paper discusses. So there are two main components of the benchmark. First is this benchmark data set, where we have examples from a variety of industries and applications of streaming data where there are anomalies, and these are labeled anomalies that have gone through a pretty strict labeling process. Also, some of them come from customers who have informed us the actual true labels of these anomalies. And it's important to incorporate real data. It's very difficult in the first place to find any data, let alone labeled anomaly data that is real. But it's important to us to include those in the benchmark because they kind of test algorithms for issues and scenarios that you can't really generate artificially.
This is really rare in anomaly detection to have real labeled data, and this is very valuable for researchers. Just forgetting about anything else, even to have this data accessible.
Well, and maybe I'll talk about it in a moment with the contest or something like that. But another thing is, once you have some data like this, other people will be much more likely to create something because they just created one labeled data set in the past. What are they going to do with it? Why bother? And now, if someone says, "Hey, I'd like to have my data set into this benchmark," I mean, it gives you a place to put labeled data and an incentive to do so. So hopefully, you'll have people creating them.
Mm-hmm. And one more note on the data. So just having the data out there is really going to spur research from industry and academia, because a lot of times you find that papers published on anomaly detection algorithms, they'll create some artificial data set or they'll have some small real data, and it makes it very difficult to compare algorithms. So you don't know who's better or who's actually doing well. And with NAB, you kind of have a consolidated data set, and hopefully we can get everyone testing on the exact same data and generate scores off of this data, which leads to the next part of NAB is this scoring mechanism that we put in place. We want to try to reward algorithms for being best at real world applications. So first we define what would be an ideal detector in real world scenarios. And we list those here. I'll go through them real quickly. First, we would like to detect all the anomalies in the data and as early as possible. In streaming scenarios, it's important to have an algorithm that can learn quickly and detect anomalies quickly. And you would like to essentially, well, rather ideally, detect those anomalies as soon as possible, so then you can have actionable information to prevent anomalies in the future.
Yeah, so if two algorithms detect the same anomaly, the one that detected it earlier would get a better score than the one that detected it later.
Mm-hmm.
And that's something that people don't typically think of, actually, in doing anomaly detection, which is kind of surprising.
Yeah, you would just have
like
a true positive and count it, but the earlier one is definitely more valuable. Going on with this list, we would prefer algorithms to have no false positives. And it's important for these algorithms to work in real time, where they're processing one data point at a time, not looking at it ahead at the data, not processing in batch, because these algorithms need to work on streaming applications. And similarly, because these algorithms are going to work across a ton of streaming applications and have a lot of sensor data coming in, they can't be tunable. So the algorithms can have specific parameters for specific sensors. It needs to be all automated. And to that effect, we've set up a NAB scoring mechanism, which includes an algorithm. I'm not going to go into too many details because the paper walks through that with some formalized math to how we get to those to the scores. But we have to test an algorithm on NAB. It'll run through every data file in the corpus and detect anomalies. And then based on where those anomalies occur relevant to our labeled anomalies, they'll fall somewhere within what we define as these anomaly windows. And that is how we are able to reward algorithms for early detections. So inside a window are true positives. The earlier your true positives, the more valuable they are. And jumping down to the results. So this paper is published in parallel with the release of NAV version 1.0. And with that, we've tested a few algorithms listed here. The Numenta HTM anomaly detector, which you can find in NuPic. Then a couple open source algorithms, Twitter anomaly detection VEC, Etsy Skyline, and then we include results with a random detector just to show that these are better than random. And it's a nice outcome that Numenta is the best performing algorithm. But you'll notice here that the score is 64.7, and these are out of 100 possible. So we left a lot of breathing room for algorithms to improve upon the best here.
Yeah, so the idea is we're just seeding it with these 3 algorithms, and we want people to try out other algorithms, and also, like Jeff said, add in more data over time, and we'll keep updating the benchmark as we get that into future versions of the benchmark.
Yeah, and also it would be great if people who the Twitter one or the Etsy one, if they came back and improved those, So it's not, again, like in the earlier, it's not to say, hey, HTM is better than this. It's just like, hey, here's the problem. Here's how you define it. Here's how you measure results, and go at it. Yeah.
And even in the NuPic community, if people want to experiment with HTMs, they might be able to do better using HTMs than we were able to do. I think there's a lot of room even within HTMs to make it better. So
good point.
And to that effect, we are starting, we're going to have a NAV competition with the WCCI, World Congress in Computational Intelligence, this July. We've posted on the website, and there are 2 themes to the competition. The first is on data. So if you're able to contribute any real world data with labeled anomalies, you can enter the competition. Then the other category is for detectors. So just like Jeff and Subutai were saying, if you can test your algorithms on NAV and prove that they're, I guess, good results, better than random, you can enter them in this competition, and we would include them in the NAV scoreboard in future releases.
Do you want to do Numenta.org session?
Is it, Matt, could you?
yeah, Numenta.org/NAV.
Go back to this and Numenta.org/NAB. So here's a description of the competition. So here's how you can get involved. If you have an algorithm that you want to add to NAB or data,
And you can win cash.
Should have led with the cash.
You should have led with the cash, Now you're talking.
It's really cash, probably a check. Who knows? Probably over PayPal, but it's money. You can win money.
It's not going to be a little coffee gift card.
Substantial rewards.
Substantial rewards, yeah.
Okay.
Is that the end of the paper?
Well, can I give a quick sneak peek on the anomaly detection paper?
Yeah, sure. That's not on the.
Yeah, that's in there. It's in the folder.
It's in the folder.
But yeah, it's not on that page.
It's not on the page.
Oh.
Yeah, that's this one.
This is a sneak peek.
Okay.
For the first time.
Anywhere
except here.
Oh, yeah. It's okay. Okay, let me share it real quick. Yeah, I have to apologize to everyone who expected to get invitations to join. Apparently, Google's not letting me invite anybody. So just sorry about that.
Okay. So this paper is really fresh. We just submitted it on Friday, and it's a blind submission, so you can see there's no authors on it. What we're going to do is put authors on it and then put it up on arXiv, just like we did with the other papers. What this paper is actually describing the. Oh, are you not sharing? Yeah. So this describes the actual algorithm that we use for anomaly detection in HTM. We've talked about this quite a bit, and we've had the code out there, but we realized that we haven't actually written down the algorithm in a formal way anywhere. So that's what this paper is. It goes over the motivation for doing anomaly detection in streaming analytics. There's a bunch of references to other techniques that have done variations of anomaly detection. And then we describe the actual way we do it. So it kind of sets up HTMs. It shows how we compute the raw anomaly score in here. And then importantly, it talks about the anomaly likelihood, why we do it and what the exact equations are that we use, if you're familiar with that. And the anomaly likelihood was really critical to converting the anomaly scores into something that's actually useful in practice. So we described the rationale for that. And then there's a new section where we talk about how you can combine multiple models. So if you have models that are doing anomaly detection on different metrics independently, this shows how you can use the equations to compute kind of a global anomaly likelihood that cuts across the different models. And then we have screenshots from our application, HTM for Stocks, which is actually doing this in real time. You can download this from the Android Play Store, so we have some fun examples of that. And then we end with the NAB score. Where is the NAB score? Here, with the same, very similar numbers to what Alex showed before. So we show both kind of qualitative results, as well as now that we have a benchmark, we can show actual formal results on that. So we'll be putting this out sometime in the next couple of weeks on the mailing list in Archive.
Okay, thanks, Subutai. Okay, back to the cam. Are there any other papers that you want to review while we're on the subject?
No, I guess the only thing, the NAB paper is a peer-reviewed publication, so that's already done. The Neuron paper and the other ones we showed you are all in various stages of process. From some we've actually received review feedback and we're working on the feedback, and the others, like the anomaly detection, is just submitted. So.
It's still a long way to go. This is a very slow process.
Yeah. Okay, so we've got a bunch of questions from Rick. So. Sorry about that, Rick. Okay, so if I could figure out which one was first.
I think it is in reverse order.
It's in reverse.
So no, that's the soonest. Yeah.
So the first one.
Way back down.
I have two ideas for a different tack on evangelizing marketing HTM technology in NUPIC. And to Mark, yeah, all these papers, except for the last one, is on our website, numenta.com/papers, and that last one will be up soon. Okay, so back to Rick. So Rick's idea is about evangelizing marketing HTM technology. Let's see, valuable invention applications. Sorry, Rick would be better at talking about this himself. So Rick's not happy with the current crop of HTM applications. They're toy size. Yes, that's true. Keep in mind, this is still like the very sort of beginning of this phase of technological advancement. So the question is, has anyone present or watching read James Maganzian's paper and have an opinion on it? I don't know how to say that. Maganzian.
I don't know who that is.
No,
I don't either.
I've never heard of it.
Second idea, take existing computational systems, try to retrofit one or more HTM concepts onto them. He personally has done this successfully, but can't go into details.
Who has?
Rick.
Rick has done it.
Yeah. I think that's a perfect example of something the community could do. I mean, we're very focused on understanding the underlying cortical principles and underlying neuroscience and trying to build those concepts into clean systems. But I think there's a lot of low-hanging fruit in taking some HTM concepts, combining them with deep learning or support vector machines or whatever, and then getting some value out of that. So that's great if the community wants to do that. I don't think we're planning on doing a lot of that ourselves.
Right.
No.
James' paper is a mathematical paper. It's a mathematical framework for HTM.
For HTM.
Yeah.
Oh, that's the spatial pooler paper.
Yeah.
Yeah, we're in the process of reading it. We actually are in conversations with him. We gave him a lot of feedback on that paper. I think it's great that he's doing that.
Sorry, James. Why did we not recognize that name? It's such a recognizable name.
Yeah.
We were so blown away by the concepts in the paper. We got his name.
I think that's great that he's working on that. We are in conversations with him separately.
We were all thrilled to see that, by the way.
So. Rick also says maybe one idea is to divide HTM into its conceptual components, those 6 concepts that Jeff always talks about of intelligent machines. and try and market them separately, which that might be kind of hard to do.
Yeah, it's hard enough to market one thing.
Well, I mean, when you say market, there's different markets. We have the scientific, we have the neuroscience community, we have the machine learning community, we have business markets, licensing opportunities. So I'm not sure which markets you're referring to, but it's a complex problem of, so we're open to all ideas. I don't think we're stuck on anything, but I'm not sure which marketing he's referring to there.
Yeah, I'm not either.
Look at Cortical. They picked up just on the SDRs. That's how they got started, right? So they picked up that one concept for starters. So there's a good example of that.
Mm-hmm. I mean, the thing is about, we'd love to see somebody come up with some killer app that amazes everyone and what HTM can do. But it hasn't happened yet. And I feel for Rick, sometimes the hackathon demos seem a bit underwhelming, but when you think about the context in which they were built, these are toy projects. You're right, they're toy projects that people are building over the weekends, and we are trying to, and we're starting to engage more companies and larger entities that have big ideas and they want to build something with HTM. Those are the things that might turn into killer apps.
So let's
we'll
just break this down a little bit further. It might be useful. The first application area we focused on was sort of streaming analytics. And then we focused inside of that. After doing that for a while, we got narrower and we said anomaly detection and streaming analytics. Now that probably is still a very large application space, but it takes time. Some markets take off right away and some don't. Well, this one doesn't take off right away. We've been working on it hard. We did HTM for Amazon, and now we have our partners picking that up, Avic. We did the HTM for stocks. We're hoping to get someone to pick that up. We now have the NAB, people paying attention to the anomaly benchmark. This could take, a long time before that really takes off. We haven't given up on it. It's slow. The next big focus for us is natural language processing. And so we're focusing on that. And that may get picked up much, much faster. We don't know yet. We're not there yet. But, it takes a while to find your killer market, your killer application, and sometimes even if you identify the right one, it take a long time for the market to be ready for it. So all I'm just saying is I'm not saying we're doing this perfectly, but we are taking this approach of let's develop one market deeply, and then we're picking another one, let's market that one deeply, and it may take that kind of focus to find a killer app. I don't know, but unless someone else can come up with something better. Would be great.
If someone else can come up with a killer app, that would be awesome.
Yes.
If anyone's listening, you got an idea for a killer app.
So we're doing our best job. We know how to do it, but we're just a small team. So a lot of other smart people out there.
Yeah, and we're not working on just building products.
Not explicitly, no. Yeah. We're trying to enable. We don't want to become an IT company or even natural language processing.
Right. On that note, Egbert, who was. I believe, if I remember your name correctly, you were one of our hackathon participants who worked on the smart port, I think, problem. He says, I hope to use it in an e-commerce engine in the coming year on personalization.
That'd be cool.
Okay, that'd be great.
Interesting. I'd love to hear what you're doing. Keep us up to date on the mailing list about it.
Yeah, kind of like there was an email thread on Nupig discussed about using it for web click prediction and web analytics. I think there's a lot of potential there as well.
Yeah, definitely. Okay, we're getting into some general questions now. Anyone who's viewing, if you have a question, please type it up. Let's see, this is from Scott Jordan, how well or not well is the union pooler working? And what were the reasons that the other attempts failed at temporal pooling?
Yeah, I don't know if failed at temporal pooling is the right word for it. I would say it's more like it doesn't have all the properties that we want. There's a video, I don't know if this video is on our website somewhere, where I talked about the history of HTMs, and included in that is a lot of the work we've done in vision and using temporal pooling and invariances there. So a lot of the early work that we did on pooling is very similar to the convolutional neural networks and Poggio's HMax stuff, where the temporal pooling part is actually hard-coded to do a max pooling thing. And then there is a convolutional setup where the weights are all shared.
This is a long time.
This was a long time ago. This is probably our first attempt at invariances and stuff. And that worked really well in certain scenarios in computer vision. If you look at the video, I showed examples of an actual product that it went into where it was able to do real-time computer vision and detecting people versus non-people and so on. So it worked pretty well in that kind of scenario, but there were a lot of issues with that whole class of stuff. and that led to the whole CLA and the new algorithms. And from a temporal pooling standpoint, that had hard-coded invariances, a very specific hard-coded invariance, and we did not want that. We believe the invariances can be learned, and the pooling itself is a part, involves learning, and so that part was hard-coded. So that was one of the things we did not like about it. Some of the more recent stuff we did, we've put out descriptions of it. Those things are learned, but they have sort of scaling issues and capacity issues and stuff like that. So those are all areas that we're feeding in. And I think underlying it all, Jeff is also really trying to understand how pooling is done in the cortex. So there's invariances and there's pooling, but there's also feedback. So the stuff that's as representations become stable, they also are used to update the inferences as well in various ways. So there's a whole bunch of different things that we're kind of working on there.
Yeah, we're not focusing on temporal pooling and union pooling as a singular thing anymore. We're trying to, I'm spending a lot of time on this, trying to understand it in the broader context of a hierarchical temporal region in the cortex. We believe, although don't hold me to this forever, but right now we believe that basically sequence memory and prediction and temporal pooling are going on in every excitatory neuron in the cortex, and so we're trying to understand the different flavors of it or how they interact, and so it's a pretty challenging problem. It's easy to come up with methods for doing temporal pooling, but getting the right one with the right set of attributes and understanding its place in the larger picture is difficult. It's exciting to work on, and I'm feeling happy. I think we're going to figure it out.
So the presentation that you were talking about, Subutai, I think was this one you gave at the HTM challenge, an HTM retrospective, right?
Yeah.
And that's where he's talking about like sort of the history of,
That's right.
of it all. So there's another question, since we just talked about kind of what you do if you have a killer app idea. Who do we contact within Numenta to talk partnerships? Well, a good place to start would probably be this page I was just on, which is the licenses page. So this describes to you what our licensing strategy is. All of the code base for our HTM implementations are AGPL, and however you can opt out of that by executing a commercial license with us. You do have to have a pretty serious idea about what you want to do, a mature idea about what you're trying to do. A prototype would be best. That's one of the reasons, our code's open source. If you want to build on top of it, you can just build on top of it. If you don't like the AGPL, there's a trial license option. You can get out of the AGPL while you build your prototype, so you don't have to worry about that. And then come to us and we'll talk commercial licensing. And there's instructions on how to do that on this page and who to contact.
I think there's a similar page on Numenta.com as well.
Is there a contact email there?
Partners. There is a contact email on that page that I just showed. Yeah. And so here's more about our current partners. If you really want to,
right. If you go up top, there's a review our license guide link.
Right here. Yeah. There we go. And then there is a license guide as well here.
But
so this will give you a good idea.
Yeah, but we're we're really interested in working with people, and if you have a real concrete idea of what you want to do, just get into touch with us using the email addresses there, and I think you'll find us very easy to work with. We want lots and lots of developers out there working on this stuff, so we want to make that happen.
Your email won't get lost. We're not big enough to lose emails. we all see every one of these.
Okay, I see one last question from John Robinson. He says, this might be a repeat, but on the mailing list it was mentioned that distal dendrites and metatropic receptors might solve some problems with temporal memory predictions that the new temporal pooling approach introduces. How might mini-bursts solve this prediction problem?
We were just talking about that today.
Yeah, we had a little research discussion at lunch today. I don't think it's worthy going into too much detail here right now, but just for those who are not familiar with this, there's these things called metatropic receptors, which make neurons do things they wouldn't otherwise do. And they make neurons be active for long periods of time, or they can force learning, they can create different growth scenarios. And we were just talking, Yue was commenting earlier today that no one's really done anything with these things in terms of computation or algorithmic analysis. And Murray Sherman, a neuroscientist, has been promoting like these things are important. Everyone needs to pay attention because they're everywhere and they change the way the neurons work. So we believe that's really important too, and we're incorporating them in our models and our thinking. It's very complex to understand it all. The specific thing about the mini bursts is that these metabotropic receptors, these long-term effective things, if you want to make a neuron do something for seconds or longer, the input, it typically requires more than just a single synapse, a single action potential at a synapse. It requires a series of very rapid ones, very close together. And that matches up with what the mini bursts do in layer 5 cells and also in layer 3 cells. So there's a mechanism by which a cell could say, do something long lasting. And that would be the mini burst. And then there's lots of questions about when mini bursts occur. So this is an area of active research. It's complex. We don't know all the answers yet, but boy, we were spending just today, we spent an hour at lunchtime talking about these very issues.
Does anyone know what the problem is that he references that was introduced by temporal pooling? Problem with the temporal memory that came about recently.
What does it say again?
It's just the new temporal pooling might introduce some problems.
Well, maybe I don't know. Maybe he's referring to the fact that temporal pooling, the activity of cells, might lead to problems in temporal memory because you don't want to have all your cells active, slowing over time. You don't get a precise prediction of the next input. They might be referring to that. Does that sound reasonable? What do you guys think?
But we think of temporal pooling happening in a different region.
Oh well, actually, I think temporal pooling is happening everywhere.
So there's a different set of cells.
No, not even different set of cells. I think it's happening in every cell.
Want to jump to the next question?
Yeah, this one.
But I don't hold that perfect.
See, he's got a follow-up question as well, which is, do you think that a feedback mechanism exists between layer 3 and 4? It doesn't seem necessary given the first-order nature of layer 4. Is the current thinking that feedback occurs only between regions and not between layers?
No, not at all. The feedback is, every layer is sending information to every other layer, and it's not clear. It's not clear which of those should be considered feedback and which of those should be considered feed forward. Sometimes it's clear, but a lot of times it isn't clear. But you can pretty much find projections from almost every layer to every other layer. It's amazing. And understanding that is tricky. Anyone else want to comment on that?
It's
you
tricky.
Can you give, there's that great little website that I use all the time that you found
Yes.
Maybe we can tell people about that. And not that it's really going to help them, it's just going to like blow your mind.
If you find it, can you post it on the Google Plus page?
Yeah.
There's a nice little live interactive website that shows you connections between layers in a rat's primary somatosensory or somatic cortex, I think it is. And so it's just one region. And it goes in tremendous detail. This comes out of the Allen Institute, I believe. And you can look at, oh, wow, what are the connections like between regions, between layer this and layer that, and this layer and that layer, and this layer and that layer, and oh my God, it's so complicated. I mean, they just present so much data that makes it look complicated. But it's kind of, if you're willing to spend time looking at that website, you can start picking out some things.
So we'll post a link in the comments and go
do we
on.
just know the name for it? We could just say search for it.
It's from the Blueprint project.
I thought the data came from the Allen Institute, no?
From Henry Mark.
Oh, okay, I got that wrong, sorry.
So let's go on to Ryan Singer's question. He says, I'm interested in using HTM to detect patterns and how users behave in software. Seems it can detect patterns, but how could an HTM communicate or present the patterns it has learned? Any thoughts on this in general? How do you get the value to the end user on that sort of thing?
Right. So we've done a few different experiments on modeling user behavior. One of the simplest ways to kind of, one of the simplest paradigms is anomaly detection in terms of communicating it to the user, because it's very easy for the user to understand, oh, something went wrong here. And so we've done stuff with rogue user behavior where we've instrumented laptops and it's counting like keystrokes and what you're doing with the file system and all this stuff, and we're feeding all of that to an HTM and detecting when anomalous behavior occurs, and then we use we have a nice UI for kind of surfacing that to the user, so you can see which to the, let's say, an administrator, so you can see which users are behaving in an anomalous fashion in a network. So that's one way. I don't know if that exactly answers your question, but that's one mechanism that we've done.
Let me take a, oh, do you want to keep going?
Yeah, another one was the web click behavior.
Oh.
So the other core capability in NUPIC is prediction. So what we do is we output a probability distribution of next things that could happen. And so in the case of, let's say, users' behavior to a website, we've done experiments where after watching lots and lots of users, thousands of users, you can do a really good job of watching a new user go through a couple of pages and then predict which 3 or 4 out of several hundred web pages they might actually be interested in. And so there you could pull out like links that automatically that suggest to the user where they might click, and that might keep them more engaged on the site if you give them good links. So that's another thing that we've done.
I was going to answer it as sort of a different, platonic level or something like that. Yeah, there's, the HTM temporal memory builds a model of a stream of data, and there's really 3 things you can do with that model. Subutai just mentioned 2 of them. The models are generally a predictive model, so the first thing you can do is you can make predictions. Anomaly detection is just doing some nice sophisticated analysis on the predictions that detect anomalies. That's the anomaly, how we do anomalies. And then the third thing you can do is classification. We started, when we first started working on the temporal memory, focusing on prediction. We found that for various business reasons, that was a harder one to sell. And so we then started doing anomaly detection because that was easier to people understand. But right now, if you look at our code base, the anomaly detection one, and then we have the NAB, benchmark, we have the code, we explain all that in great detail. The prediction stuff, we did a fair amount of work on it, but we didn't explain it as well. And I don't think we have as much, we did a lot internally, but I don't think it's as well documented or tell me if I'm wrong.
There is the hot gym prediction example in NUPIC that people can leverage, and then there's the stuff that UA showed on.
Maybe.
But it's not
as easy, I think, but you can do it. And then Subutai did some work in classification, and that's the one we have developed the least, but it's doable. And so those are basically the 3 categories in which you can work with. And all I'm pointing out is that some of them are easy to work with today because we do a lot more work in them than others.
And there's always a problem of scalability with this too, if you're trying to do analysis of how your users of your software. And one of those examples, as Subutai mentioned, you might have one model that represents the usage patterns of sort of all the users aggregated together. It'll give you the most feasible directions they're going to go next, and that's just one model. That scales pretty well. Yeah. But if you're going to make a bunch of different models for like different dimensionalities of your users or something such like that, you might want to have female users versus male versus different countries use it in different ways. You're going to have a model for each one of those somehow. And
that's an opportunity. That's an opportunity to do better.
Yeah, definitely. All right, thanks, Ryan. One more question we have, last chance for questions. We're out of time pretty much. Sebastian asks, have you made any experiments with feedback from the CLA classifier to a lower module like an encoder?
No.
Well,
I don't, what would we want to?
You mean something like semi-supervised, where you have a label kind of feedback to the model, and then you can improve its behavior.
Okay.
We did some experiment with feedback. That's not using the classifier, but we in those experiments we assume we know the name of the sequence and use that information to improve the
Yeah, we did do feedback with, so this is after temporal pooling, you have a stable pattern representing a sequence, and if that is fed back to the temporal memory, you can, now because the sequence label is more stable, you can be robust to a lot of different types of temporal noise that you wouldn't otherwise be robust to. So that's going from a higher level to a lower level of HTMs. But it doesn't involve a classifier or an encoder directly.
And that one, is that code out there, or is that just our little research?
It's in the research repository. It's not terribly well documented, but it's there.
Yeah. I mean, the work we're working on now, we should really get to the heart of this. Less to the encoders, but more to like in a hierarchy. You know, the general goal of a hierarchy, one of the goals is to basically take higher level concepts and drive either predictions or behaviors in novel ways, but down the hierarchy. And key to the whole hierarchical representations.
But we haven't done anything semi-supervised or even directly supervised like in typical machine learning, but that could be if someone wants to try to put some of those techniques together, that could
That'd be really interesting, yeah.
All right, it doesn't look like we have any more questions, and the entire office hour is up. So thanks everybody for watching. If you liked this video, please press like and subscribe to our YouTube channel. That lets us know that we should continue making these things. And
It's a button right here, right?
Yeah, that's like right down there. But no, I gotta do this. There's one more question, last question from Rice Singer. It says, your answer helped me see that I'm asking about classification. Say an HTM learns songs and you play many songs that are more different or similar. Is it conceivable to inventory how many songs or common themes it has recognized?
So you
Sure, it's conceivable.
yeah,
Yeah,
it's
absolutely.
conceivable.
We didn't do that, but yeah.
It's in this. It's in it somewhere. It's in it out. It's hard, right?
Yeah, the thing that's going to be hard, so you can use the stuff that we have today to do it, but the thing that's going to be hard is to maintain classification even though the inputs are noisy and even though the inputs are variable. And for that, I think you really need some sort of temporal pooling or some invariance layer to do that properly. So you could take a CLA classifier and feed it the inputs today and classify it. And if it sees the exact same patterns again, it's going to recognize it. But as you add more and more variations, if you want to be really good with respect to classifications, then you will need something like pooling or invariances or some other technique.
And really to solve this problem in a big way, I think you're going to need some hierarchy too. Well, it comes along with the pooling.
Yeah, you have to ask the question, how does it, like, what do you mean by similar? How would it know that they're
Yeah.
similar? Right now, our temporal memory is explicitly trying to make them not similar.
Right.
Yeah.
I mean, doesn't it seem fitting to put a clustering on top of it?
No, because the temporal memory is going to give you a completely distinct representation, even if it's the same exact input pattern in two different songs. So what you really need to do is have hierarchy, have some way for it to know that things are similar. Whether it's,
Yeah, I think that's right. I think you're going to need hierarchy to do a really good job at this. And you're right. The real question is similarity. What does it mean to be similar? You know, there's spatial noise, there's temporal noise, there is an invariance like in a different key. There's a lot of things that come along, and then it's like, oh, this is country music, or this is, sounds like, Beyonce or whatever. I don't know.
Yeah, but it'd be interesting to see some experiments along those lines. If there are specific problems that people think should be solved, it'd be great to see code around that and some examples.
A Beyonce encoder. Anyway.
She's not similar to anyone, that's the problem.
No, Fergie, maybe Fergie. Okay, sorry everybody, I'm digressing. Thanks everybody for joining. We'll see you guys on the mailing lists. Take care.
Bye.
Bye.